Okay, so I welcome you all to this new course on fundamentals and applications of dielectric ceramics. My name is Ashish Garg and I am working here as a professor in the Department of Material Science and Engineering at IIT Kanpur. So this is a course basically primarily aimed at undergraduates of primarily material science and engineering, ceramics engineering. It could also be useful for undergraduates of physics, chemistry, electrical engineering, mechanical engineering. Anyone who wants to work in dielectrics or wants to gain knowledge of dielectrics can do this course. As such, there is no prerequisite. If you have understanding of 12th level physics, that should suffice to do this course. So let me now go to some contents of this course, what you are going to learn over a period of 8 weeks, and the contents are that we will learn in this course include the bonding and structure of ceramics. So this will go for about 1 week. We will not touch too much about bonding and crystallography. We will just straight away jump to the structure of ceramic materials, but we will have some primer on what is bonding about and what is crystallography about, perhaps in today's lecture. And then we will move on to a very important topic in ceramics, which is defects in ceramics. And defects in ceramics are very important to understand. Defect chemistry, especially if you defect in dielectric ceramics, not in ceramics. Well, dielectrics are ceramics also, so it could be more generic. So this we will do over a course of week 2. Okay. So here we will talk about what kind of defects that prevail in dielectric ceramics, what happens when you add impurities to them, what happens when you change partial pressure of oxygen, because most of them happen to be oxides. As a result, when you change oxygen partial pressure, there is a tremendous influence on the characteristics or properties of these materials. And then we will shift to move to what we call as linear dielectrics. And linear dielectrics are those dielectrics whose polarization behavior as a function of electric field is linear. And here we will first look at the basic mechanisms of dielectric materials. We will look at what is polarization and its mechanisms. Then we will look at what is polarizability. We will look at the frequency dependence, and of course dielectric constant here, that is also an important bit. Frequency dependence of above, and then we will look at impedance analysis, because it is important to analyze the impedance spectra of dielectric materials to understand their behavior completely, and then we will perhaps look at certain applications. So this will constitute about 2 weeks, which is week 3 and 4. There could be some overlap that is possible between weeks, but we will try and stick to our schedule. And then we will move on to what is called as nonlinear dielectrics. We will see what these what is the meaning of linearity, nonlinearity in the subsequent course of time as we learn about it. And in this case, we will learn about what are the basics of above materials. Then we will look at the classes of materials. We will discuss each of them. So we will start from piezoelectrics, then we will go to pyroelectrics, and then we will look at finally ferroelectrics. All these 3 materials are technologically extremely important, and that is why it is important to understand the fundamentals of these materials, the classes of these materials. And then we will look at, so this will constitute for about 2 weeks. So this will go from week 5 3 weeks, week 5, 6, 7. Okay. There is a possibility that there is a spillover from the previous weeks a little bit. So, there could be certain overlap, and then we will look at what we finally we will move on to ferroics and multiferroics, and there we will basically introduce this new topic of multiferroics, looking at the types of multiferroics, what are the materials, what is the importance of these materials, and what are the challenges, what is the current status, and this will constitute week 8. So, this is the overall overview of the contents of the course that we will undertake as we progress in this course. Now, let me go to the bibliography. What are the books that you are going to follow? And here I would say the first thing is essential bibliography. So, these are the books that you require for yourself. So, first will be physical ceramics, principles for ceramic science and engineering. This is a book written by Y.M. Chiang, D.P. Burney and W.D. Kingeri, and it is published by Wiley VCH. So, earlier first few chapters, especially from the perspective of structure, bonding and defect chemistry. Okay. So, these are the topics which this book covers well. Then we will look at another book which is called, whose name is Principles of Electronic Ceramics by L.L. Hench and J.K. West. This is published by Wiley. This is a book basically for learning about linear and non-linear dielectrics. This is a very good book for learning the basics of electronic properties or electrical characteristics of linear and non-linear dielectrics. We may also look at electroceramics, materials, properties and applications. This is by J. Moulson and J. M. Herbert, and this is again Wiley published book. Again, this is good from the perspectives of properties of ceramics and applications. And from the perspective of defect chemistry, there is one very specific book that I would recommend to you. If you have time, you can read it. That is non-stoichiometry, diffusion and electrical conductivity. In binary metal oxides by P.K. Kofstad and this is again basically John Wiley and Sons. This is very good from the perspectives of defect chemistry. So, those who want to improve their knowledge of defect chemistry can read this book. So, these are the books that we will follow. The first book, Physical Ceramics by Chiang, Burney and Kingery, from the perspective of structure, bonding and defect chemistry. Then we will look at electronic ceramics, principles of electronic ceramics from the perspective of linear and nonlinear dielectrics by Hench and West. And we may also refer to electroceramics, materials, properties and applications by Moulson and Herbert from the perspective of properties and applications. If you are interested in defect chemistry, you can look at this book by Per Kofstad or P.K. Kofstad, that is non-stoichiometry, diffusion and electrical conductivity in binary metal oxides. And then there are a host of other books which you can, so I can just say that, you know, supplementary reading. So, supplementary reading could be from the perspective of those who do not know solid state physics. They can read solid state physics by, so the first book would be Kittel. This is a very famous book. Then would be A.J. Decker. So, this is Charles Kittel, this is A.J. Decker, and then one can also look at and Ashcroft and Mermin. These are three books which will provide you good understanding of basic solid state physics of materials. And then if you are interested about material science basics, then I would say material science, basics. I would say the first thing would be to read the book of V. Raghavan, which is a very nice book giving you complete information to begin for the beginners about material science. Then we have Callister, W. Callister or W. D. Callister. This is again similar book to Raghavan, but I consider Raghavan a little better in terms of its content. And then we have Wolf series. So, this is a 4-volume series. We call it Wolf series, but basically it is a material science engineering series from MIT, 4-volume. It is a very old book, but it is a very nice book to read about. So, these are the books you can read about improving your material science fundamentals, and these are the books you can read about improving your solid state physics fundamentals. So, now so as I said, the prerequisite for this course is basically nothing significant. If you know basics of structure of materials, basics of thermodynamics, basics of solid state physics, you will do well in this course. So, the supplementary books that I recommended are the ones you can read and improve your knowledge. And this course is suited, as I said, for final year undergraduate students or third year undergraduate students of most disciplines, including material science engineering, chemical engineering, mechanical engineering, physics, chemistry, electrical engineering, and so on and so forth, and also for fresh graduate students and like masters and PhD students. So, now let us begin with our course content, the first lecture contents of this course. So, this initially the first module is about, so the first week that we are going to discuss is going to be on basically structure and bonding in dielectric ceramics. Now, essentially what dielectric ceramics are mostly oxides. So, dielectric ceramics are mostly oxides. Oxides are materials such as, so oxides are generally mixture of cations and anions, and so cations are generally more so cations have tendency to give away their so electropositive I can say, and these are electronegative. Okay. So, cations have tendency to give away electrons, anions have tendency to accept the electrons, and the difference in the electronegativity is a driving force to form a bond between the cations and anions. So, the formula, so you can have binary oxides. So, basically the difference in the electronegativities of two types of elements drives the type of bonding that you will have. So, generally oxides you will find they are either covalent, either ionic or strongly ionic or partially ionic with covalent character. So, generally this is the bonding scenario in these materials. So, you may have types of materials as these oxides could be you can have binary oxides, of the form MO, and so for example, things like formulas would be MgO, NaCl, NiO, all these are binary oxides. You can have ternary oxides, which we can say, so binary oxides could be MO, it could be M2O3, it could be MO2 and so on and so forth. So, M2O3 could be something like MOO3, WO3, sorry, Al2O3, Cr2O3 and so on and so forth. MO2 could be TiO2, ZrO2, all these are MO2s. You can have ternary oxides. Ternary oxides can be, you can say, let us say AbOX. Okay. So, for example, your barium titanate is a ternary oxide. So, you have barium as a cation, cation 1. So, this is M1, titanium is M2, or you can say A, B, and then of course, U which is O, which is the anion. You can have quaternary oxides. Example could be strontium bismuth tantalate, SrBi2Ta2O9. So, in this case you have 3 cations and 1 anions. So, there are possibilities of multiple kind, but generally we deal with the oxides which are binary or at the most ternary in nature. There are very few examples of quaternary or penternary oxides that we use in literature. Now, given these oxides have, given these materials have oxygen in them, they are strongly influenced by oxygen content in these and the oxidation states of these elements that are present in them. Many of the elements tend to be transition elements which have tendency for valence fluctuations. As a result, there are multiple valences present in the same material. As a result, you may have non-stoichiometries that we will deal in the defect chemistry. So, and these cations and anions in these materials are present in sort of, so there is atomic arrangement that is there. So, atomic arrangement of cations and anions gives rise to what we call as all of them have a certain crystal structure, and they have certain symmetry, crystallographic symmetry and space group, which defines their structure and properties. So, what we will do is that we will first begin with certain fundamentals of crystal structure before we move on to the structure of these materials. So, these materials, as I said, so atomic arrangement of cations and anions determines the crystal structure. As a result, they have certain symmetry, certain space groups, which is important in imparting certain properties to them. Now, what are these materials useful for? Dielectric materials are useful for a variety of applications. So, they are used for various applications such as sensors, actuators, data storage, transducers. So, sensors, actuators, transducers. So, sensors means they are used for sensing. Okay. So, it could be sensing gases, it could be sensing displacements, this could be sensing stress. So, sensing any kind of stimuli. Actuator means providing actuation. So, actuators and transducers are the devices which are based on utilizing the mechanical movement in these materials. So, we will see these are very important. So, certain types of dielectrics, not all dielectrics can be used for these purposes, but only certain types of dielectrics are used for actuators and transducers kind of applications. They are also useful for data storage, because many of the DRAM materials, for example, DRAM materials are conventionally made on silicon oxide, but there are a lot of materials which replace silicon oxide, such as hafnium oxide, you have tantalum oxide, you have zirconium oxide, yttrium oxides, and here the property that is important in these materials is dielectric constant. So, dielectric constant of the material is exploited to make these thin films and these dynamic random access memories for storing the data. They are also used for, they can also be used for optical devices, because these dielectric materials have certain optical properties which can help them work in these devices, but we will not deal with the optical properties. And there are materials such as barium titanate, lead titanate, and so on and so forth, which are nonlinear dielectrics, which are used for these sensors and actuators kind of applications as we discussed above. So, there are a lot of applications of these materials, and as we go along the course while describing certain classes of materials, we will look at some of the applications in a little bit detail. So, this is what the brief intro of dielectric materials is. Now, let us go to nitty-gritties of what structure of these materials. We will first discuss the structural aspects of these materials. So, now, by structure here I mean, so a structure can be defined at various scales. You can have electronic structure, which is the structure at the electronic level. You have atomic structure, which is at the structure at the atomic level, and then we have structure at the micro/nano level, which is basically microstructure or nanostructure, and then we have what we call as macrostructure. So, this is at the electronic level, electronic structure. Atomic structure is the level of atoms. Nano or microstructure is at the level of microstructural features such as grains, grain boundaries, and so on and so forth, and then macrostructure is in the form of the shape, the pores, the voids, the shape, etc. So, here when we talk about the structure of ceramics, we are mainly concerned with the atomic structure of these materials. So, this is what we are going to talk in next few slides. So, as far as structure is concerned, the first important thing you need to know is what is called as lattice. Lattice is basically, you can say, periodic array of points in space with identical neighborhood. Okay, so this is basically is point lattice, right. So, any kind of arrangement like this, where each point, you have a periodic arrangement of points in space, and each point, whether you look at this point, whether you look at this point, whether you look at this point, all of them have identical neighborhood. This is called as point lattice. You can have this kind of arrangement also, but this will not be a lattice, because each point does not have identical neighborhood. So, this is a lattice, this is not a lattice. Okay. So, this is the first concept. that a point lattice has regular arrangement of points in space with identical neighborhood. It is periodic, identical neighborhood, and then it has regular arrangement of points in space. This is what is a point lattice. There are possibilities where you can make lattices which have sort of very nice looking arrangement. So, for example, if I make this arrangement here, so I will not draw too many. So, I will just draw it using a different color. So, if you just go down one more point here and another point here maybe. So, all these points have equal spacing with respect to each other, sort of hexagonal. It is sort of distorted here, but it is sort of hexagonal network. But if you look at this point A and this point B, the neighborhood is not identical. For A, you have one point on the right, 2 points on the left at certain angles. For B, you have 2 points on the right, 1 point on the left. So, this is not a point lattice, even though it looks like a regular ordered arrangement. However, if you have arrangement something like if I make this kind of arrangement, let us say, and I put points here, 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 here. And additionally I put points at the center. Then whether I look at point A or B, all of them have similar neighborhood or identical neighborhood, which means this is a point lattice. So, basically a point lattice is a regular periodic arrangement of points in space with identical neighborhood. This is the definition of point lattice, and within a point lattice you can create what we call as unit cell, which is a smallest repeatable unit. Okay. So, within this you can create a unit cell, something like that. So, this is unit cell, and unit cell has certain parameters which are called as length and breadth and angles. So, unit cell has unit cell parameters. So, we define them as A, B, gamma in case of 2D, and in case of 3D we define them as A, B, C and alpha, beta and gamma. So, these are called as unit cell parameters. Now, the choice of this cell is not unique. You can make any shape unit cell. So, for example, in this case you can make this as a unit cell, but it is also possible to make this as a unit cell. So, this is also a unit cell. Okay. So, this is where the question arises is what kind of unit cell shall we choose. So, this is determined by what we call as symmetry considerations. So, based on the shape and lattice parameters we define and the symmetry. So, if you add symmetry considerations plus symmetry, and there are certain symmetry operations which each which have to be performed. These symmetry operations are translation, rotation, reflection and inversion. So, if we perform these symmetry operations, then what we generate is what we call as crystal systems. So, then we we do not have indefinite so as I said, choice of unit cell is not unique. Okay. And you can see from this picture, this contains one lattice point, because you can see that all the four corners have four points which are shared by neighboring unit cells. As a result, we have one point in the unit cell. Similarly, in the neighboring one, we again have one point in the unit cell. So, they have same area, they contain one lattice point. If you contain something else, that will also be similar. So, as a result, choice of smallest lattice unit cell is, so it is also possible to choose a different shape. So, you can have multiple shapes, they will be similar in area and they will contain only one lattice points. So, that is why you have to evolve a system which is called as crystal system, but that takes into consideration the aspects of symmetry that we will discuss in the next lecture. Thank you.